So it gives me a great pleasure to introduce our speaker today, which is Takayuki Hibi, who's on a Canadian tour. He's been at McMaster this week, and he'll be at Fields next week, and he's off to Halifax the week after. So he's doing the great Canadian tour, and he's giving us our talk in our learning seminar today about polytopes. Okay,
Yeah.
Go ahead, take it away.
Oh, thank you very much. I'm very happy to give a talk here. And today, this is a learning seminar. So my talk is counting a lattice point in lattice polytopes. So I start with a Pick's formula. Maybe this is well known. And first of all, a point A1, AD, RD is called a lattice point if each AI is an integer. So lattice point is just an integer point. Yeah. And the lattice polytope is a convex polytope. Each of whose vertices is a lattice point. Yeah. And so we consider lattice polytope in RD. Then today, important number is BP. BP is the number of lattice points belonging to the boundary of P. And CP is the number of lattice points belonging to the interior of P. Yeah. So B is the number of boundary points, and C is the number of interior points. Yeah. This is I want to discuss these 2 points. Yeah. And the classical formula of Pick is okay. So Pick's formula is a 2-dimensional case. So in this case, just for elementary school mathematics in elementary school. So P is a lattice polygon, and BP is again number of lattice points in the boundary of P. So in this case, BP is a number of green points. This is boundary is here, boundary is here, boundary is here. So this is now a green point. So number of BP is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, BP is 10. Yeah. And CP is the number of lattice points belong to the interior of P. So interior is this red point. So 1, 2, 3, 4, 5, 6. So in this case, BP is 10 and CP is 6. Yeah. And the Pick's formula says we can compute the area of this lattice polygon in terms of this BP and CP. So this is the Pick's formula. Yeah. So the area of P is half of B plus C minus 1. So this is the classical formula on Pick's formula. Yeah. And in general, this cannot be, we cannot make a formula for in higher dimensional case. This is exactly 2-dimensional case. Yeah. But nevertheless, what can be said about B and C for higher dimensional polytopes? This is today's theme. Yeah. Okay. And first of all, I want to discuss L-hat theory. This is interesting, and this is very much related with commutative algebra. So always okay, P is a lattice point of dimension D. Always P is a dimension D, and in RD, P is a lattice point of in RD of dimension D. Okay, and n times P is direction of P. So n times P is n alpha. Alpha is contained P. So if P is this and 2P, 3P, 4P, something like this. And we are interested in the number of lattice points contained in the n times of P. So this is IP to n times P. And I star P is the number of lattice points of n times interior of P. Yeah. So these two points is counting. Yeah. So thus in particular, so IP1 is the number of lattice points contained in P. So this is boundary plus interior. And I star P1 is number of lattice points contained in the interior of P. So this is exactly C. Yeah. Okay, so again, once more again, CP is very important. BP is the boundary lattice point, number of boundary lattice point, and the CP is the number of lattice point in the interior. Okay, so okay, then Eilhart was a high school teacher in France, Strasbourg, and okay, so Eilhart so this function IPN is a polynomial in n of degree d, and the constant term is 1. Yeah. Okay. And this IPN, number of lattice point in n times p, and the number of lattice point in n times interior, this is related to this kind of thing. So since IPN is a polynomial, we can put minus n for n, and minus 1d. This is exactly I star Pn. Furthermore, the quotient of nd of this polynomial IPN is equal to the volume of P. So maybe Pn, so Pn R3 is a lattice polytope of dimension 3. Vertex is 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, m. Then IPN, number of lattice point contained n times Pn is something like this, and the number of point contained with n times interior, n times interior of P is something like this. Yeah. So this IPN and I star Pn is related with like this or like this formula. Yeah. Exactly this is the plus and this is minus. This is the plus and minus, and this m over 6. This is the volume of this polytope. Volume of this polytope is the quotient of this m over 6. Yeah. Okay. And now, so we are interested in this number of lattice points contained in n times p, but in combinatorics, we often consider the generating functions. So this is 1 plus, so IPN lambda n, yeah, 1 to infinity. This is the so-called generating function of IPN. But since IPN is a polynomial in n of degree d, so times 1 minus lambda d plus 1. Yeah. And expand this delta n lambda n. Then, since IPN is a polynomial in n of degree d, so this delta n equals 0 for all n is bigger than d. So this is in commutative algebra. This is Hilbert function, and this generative function is a Hilbert series. Yeah. And also Richard's standard shows that each delta I is non-negative. Yeah. 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 Okay.
Is the IP n defined for 0? Or is that why you have a 1 at the beginning?
Because what IP0? IP0, this is the constant term is 1. Constant term is 1. Yeah. Oh, yeah. So what is the IP0? Yeah. So I don't want to define IP0. Yeah. But constant term is 1. Constant term is 1. So this is constant term 1. Yeah. Of course, we can define IP0 equal 1. Yeah. This is just point. This is just point. Oh, yeah. So this is generative function, and so this sequence delta 0 delta d is called the delta vector of P. So in commutative algebra, this is so-called H vector of Hilbert function. Yeah. And so in particular, delta zero is a constant term equal to 1. And delta 1 is a quotient of lambda is IP1 minus d plus 1. And this is delta 1 is IP minus 1 minus delta 1. And IP1 is the number of integer point contained in P. This is the boundary plus interior. So delta 1 is B plus C minus D plus 1. Yeah. And also, by using this relation between I star Pn and IPn, so one can prove that. So delta D is IP1, this is Cp. Yeah, we can prove this. And also volume, what is volume? What is volume was? So volume is a quotient of ND, higher powered is equal to the volume of P. So volume of P is a quotient of ND. So this means volume of exactly sum of delta vectors over d factorial. Okay. So in any case, we can compute the volume of this. Yeah. So if we know this L hat polynomial, then we can compute the volume of P. Yeah. But degree of D, so we cannot compute this IPN in terms of B and P. Yeah. We need more information. Yeah, to decide IPN. Yeah. Okay. And this example, in this IPN, in this example, delta Pn is 1, 0, n minus 1 and 0. Yeah. And so delta vector is always non-negative, but quotient of IPN, this must be negative if m is bigger. Yeah. So usually quotient is not necessarily non-negative, but delta vector is always non-negative. Yeah. Okay. Yeah. Okay. Then, yeah, this is one of the basic theorem. I was proved this when I was almost 30 years ago, or when I was young. Yeah. So PRD is the lattice polytope of dimension D, and suppose that delta P. So recall that delta P is Cp. This is number of lattice points in the interior of P. So is positive. So P has at least one lattice point in the interior. Then its delta vector, this satisfies delta I is always bigger than or equal to delta 1. For I equal to 3, d minus 1. Yeah. Okay. And what this means? Once more again. So delta 1 is C plus D, B plus C minus D plus 1. Boundary interior minus D plus 1. And delta D is just interior Cp. And the volume is sum of this. Okay. And these three things together with this lower bound theorem implies that we have here. So volume is sum of delta over d factorial. Okay, and delta 1 is d minus and each delta I, each delta 2, delta d minus 1 is bigger than or equal to delta 1. So volume is less than d minus 1 times delta 1. Yeah. So delta 2, delta 3 is bigger than or equal to delta 1, this. Yeah. And delta 1 is b plus c minus d plus 1. And delta d is c is equal to d minus 1 b plus dc minus d square plus 2 over d factorial. Yeah. Yeah. But so in general, if delta P is positive, Cp is positive, if P has at least one lattice point in the interior, then volume is always bigger than or equal to this d minus 1 Bp plus d Cp minus d square plus 2 over d factorial. But when d equal to, d equal to case is this half of b plus c minus 1. So exactly a Pick's formula. So if d equal to case, this is exactly a right hand side of Pick's formula, and d equal to case this is just equal. But in general, this is just lower bound of the volume. Yeah. What?
Yeah. Question. Is the delta D, does that ever greater than equal to 1 as well? Are there like the number of interior points bigger than the delta 1? Does that ever happen?
Yeah. Oh yeah. Or BB. Oh yeah. Sure. Yeah. Oh yeah. Delta one is B plus C minus D plus 1, and B is always boundary is always at least D plus 1 because this is dimensional. D dimensional. Yeah, and delta y D is CP, so B1 is at least bigger than D delta D. Yeah. Mm. Yeah. So this is, in some sense, this is a higher dimensional version of Pick's formula. Yeah, but unfortunately, we don't have this is not equal. Yeah, but this is something like higher dimensional case of the right hand side of Pick's formula. Yeah. So this is so-called lower bound of the volume. Yeah. But what this means? What this lower bound means? This is interesting. What this lower bound means? Yeah. So we need some background of algebraic geometry. But this is just a brief summary because I myself cannot understand what is this background. Yeah. But nevertheless, we must talk about this. Yeah. Okay. So this is also almost the key point is this is so 30 years ago. So this result was 30 years ago. Again, I need one more result for 30 years ago in algebraic geometry. So So just a brief summary. Yeah. So X be a complex projective variety of dimension D and L ample line bundle. Yeah. And ample line bundle is something like define embedding of X in projective space. Yeah. And this L is L plus 1 is like H0L. And the polarized variety is a pair of a complex projective variety and ample line bundle. Yeah. Of course, I myself cannot understand what the definition of ample line bundle was. So, yeah. But nevertheless, I need to write this formula. Yeah. And suppose that H0L is bigger than D plus 2, and that L is very ample. Yeah. Okay. And don't ask me what is very ample. Yeah. What is very ample? Yeah. Okay. Yeah. Then again also this point again also this 30 years ago. Japanese algebraic geometer Takao Fujita gave an upper bound of the sectional genus. Yeah? And this is the higher dimensional version of the Castelnuovo bound. Yeah. And what is this Fujita's upper bound? Fujita's upper bound is Fujita's upper bound is something like this. Okay. And I want to discuss the detail. I don't want to discuss the detail of this. In any case, I need this something like some invariant is less than or equal to some invariant. This is important. Yeah, each invariant is I don't care about each invariant. important is some invariant is less than some invariant. So LD is degree of embedding, and M is something like this. And delta XL, this is so-called delta genus. And this GX delta is sectional genus. In any case, this sectional genus, some invariant is less than or this number. And this is upper bound of GXL, sectional genus. And Takao Fujita, okay. One called XL, this is Castelnuovo. Yeah, if this H0L is bigger than equal to D plus 2, and L is very ample, and the equality hold in 2. Okay. Yeah. Yeah. Once more, yeah, okay. Yeah, so this is polarized variety. Yeah, and suppose that H0 is D, at least D plus 2, and L is very ample. Under these two conditions, Takao Fujita show that this inequality. Yeah. So this condition, H0L is D plus 2 and very ample, and this is equal. Then call this is this polarized variety is called Castelnuovo. Yeah. Okay. So this is the algebraic geometry. Yeah. Okay. And so this is related with convex polytopes. We consider the toric variety. So again, then PRDB are lattice polytope of dimension D. Yeah. And then we can define a so-called fan from P. Yeah. And X equal toric varieties defined by of sigma and LP, the ample line bundle on X. Yeah. And polar toric variety is a pair X and LP. And it's interesting. This polarized toric variety, XLP and P is a one-to-one corresponding. X and P is not one-to-one corresponding. If we have P and 2P, then both things are defining same toric varieties. Yeah. But if consider the X and LP, then this polarized toric varieties are one-to-one corresponding between lattice polytopes. Yeah. In this case, H0LP, we call that what is H0LP? Yeah, H0LP. Oh, what is H0LP? Yeah, H0LP. This is the ample line bundle define embedding X to Pn, and this N is H0L equal An plus 1. Yeah, and this H0L is computed in the toric variety case. Yeah, something like this. So H0 toric variety case is this BP plus CP. Yeah. And always BP is bigger than number of lattice point in the boundary is since P is dimension D, at least D plus 1 and CP. But plus CP, so H0LP. Yeah. So, and okay, so suppose that CP is positive. Yeah, CP is possible. Then H0LP is bigger than or equal to D plus 2. D plus 2. And when we discuss Fujita formula, we must require H0 is at least D plus 2. Yeah. Okay. And okay. Yeah. So if HCP is positive, then this H0LP is at least D plus 2. Yeah. So we have Fujita situation, and CP is possible. So this is we have a volume lower bound theorem for volume of P. Yeah. And furthermore, Fujita inequality is so. Furthermore, suppose that LP is very ample, then Fujita formula is something like this. Okay. If we discuss Fujita formula, we need this condition, H0 condition, and very ample condition. Yeah. If we suppose these two conditions, then this is Fujita's inequalities. And this is lower bound inequalities of volume. Okay. So this is our situation. Yeah. Okay. Both are, this is 1994, this is 1990. So 30 years ago. Yeah. But this is the volume of P, and this is toric variety inequality of toric varieties. So then now recently, yeah, Kawaguchi show that. So suppose that CP is a lattice polytope of dimension, and CP is the number of lattice points in the interior. So P has at least one lattice point in the interior. Then he proves the following conditions. So XLP is Castelnuovo. Okay? XLP is Castelnuovo is by definition. So H del LP is this condition, and LP is very ample, and this is equal. This is XLP is Castelnuovo. Castelnuovo is, this is at least D plus 2, this is very ample, and this is equal. Then we call XLP as Castelnuovo. Okay? And this is XLP is Castelnuovo if and only the equality fold in 1. So equality is 1. So essentially, this equal is equivalent to this equal. This is equal if and only if this is equal. So this was proved by Kawaguchi. So now this inequality has some meaning in algebraic geometry. And Takayuki called XLP is Castelnuovo if this condition and this condition, this is equal. And this is equivalent to the equality fold in 1. There this lower bound inequality. Yeah. So by using this theorem, so we can define a lattice polytope P over RD of dimension D with CP possibly is called Castelnuovo. Okay. If the equality fold in 1, in other words, volume of P is this over D factorial. So always by using Pick's formula, dimension 2 case is always Castelnuovo. So this is the reason why this polytope we call this is Castelnuovo. Yeah. But of course, Castelnuovo has nothing for polytopes. Yeah. Okay, so this is very new notion of polytopes, and what we can say about Castelnuovo polytopes. Yeah. So Castelnuovo polytope. So Pick's formula so that every lattice polygon is a Castelnuovo if CP is possible. And the interesting case is the unit cube. This plus minus 1 plus minus plus 1 in RD. Of course, this is the origin is contained in the interior. This is Castelnuovo if and only D is less than or equal to 3. In a higher dimensional case, this cannot be a Castelnuovo. So this cannot be. And so this is just every Castelnuovo polytope has a regular unimodular triangulation. Okay. Something regular unimodular triangulation is come from gravimetric base triangulation coming from gravimetric base. Yeah. So Castelnuovo polytope has quite nice properties. Yeah. Okay. Example, to construct a Castelnuovo polytope is not so easy, but this is one example. Yeah. Simplex of dimension D. This E1, En-1, this is unit coordinate vectors in RD. E1, oh no, this is ED. No, it's not, this is not D. E1, ED minus 1, and ED. This is unit vector. So this vitality to this E1, ED minus 1, and C times E1, ED plus ED. C is positive integer. Then this is P is Castelnuovo, and in this case, the number of boundary point is D plus 1. So this is just simplex. Okay. And the interior point is C. So delta vector is 1, C, 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 C. Yeah. So this is simplex case. And this is so this is the boundary number of boundary point is D plus 1. This is the least number, and interior number of interior lattice point, yeah, is C. And also we consider next prism. Yeah. This is the basis is E1, ED minus 1, W. The W is minus E1 minus ED minus 1. Yeah. So three-dimensional case is 1, 1, 1, minus 1, minus 1. And E1 plus C plus 1 D and ED minus 1 plus C plus 1 ED. So if we have a base point and the prisms are something like this. Okay. And okay. So W plus C plus 1D. So this is high, C plus 1D, C plus 1 ED, C plus 1 ED. Yeah, so this is prism. Yeah. So in this case, number of integer point in the interior is again C. So this is same. This is also number of integer point is C. But number of the boundary point is CD plus ND plus 2. And this is also Castelnuovo. Yeah. So interior point is C. Interior point is both are C. But boundary point is this is D plus 1. And this is CD plus ND plus 2. Yeah. And we can construct by this prism and so simplex. Yeah, we can construct fixed number C if we fix C. And the boundary point is starting from D minus 1 and to CD plus 2D plus 2. Yeah, we can construct. Yeah.
I guess a hard problem is classifying the delta vectors that are Castelnuovo. Like,
oh yeah, but yeah. But classify delta vector of Castelnuovo polytope is exactly classify B and C. If we know B and C, then we know the old delta vector in Castelnuovo case. Yeah, so B and C, this is pair. What we can say about this pair? Yeah, so the
How many reflexive parts?
how many reflection?
Reflexive.
Reflexive is just 1, 1. Yeah, reflexive Castelnuovo. Yeah,
So you said the cube, that was one of them, right? In dimension 3, but then it's not in higher dimension.
Oh, not higher dimensional. Oh, this is always, yeah, reflexive. Yeah, but just 3-dimensional. Yeah, so higher dimensional. So the question is we define delta vector. If we know the delta vector, so triplet of integer B, C, D. And B is the number of boundary point. B is at least D plus 1, and C is positive, and D equal to is coastal Castelnuovo triplet. If there exists a Castelnuovo polytope P of dimension D with B is the number of boundary point, C is the number of interior point. So this might be a most interesting question on Castelnuovo polytopes. Yeah. In this case, Castelnuovo case, if we know B and C, then we can compute delta vector. Yeah. And so in dimension 2 case again, yeah, when D equal 2, Scott found 1976, Scott found all the Castelnuovo triplets. The Castelnuovo triplet with D equal 2. D equal 2 is B1, 2, B is between 3 and 9, and yeah. If C or BP, or C. If the number of lattice point is 1, if number of the lattice point in the interior is 1, then B is between 3 and 9. But if number of lattice point C is at least 2, then B is between 3 and 2C plus 6. Just one just one, this is 9. But this, if we put this C equal 1, then this is 8. So we need some situations different between 1 and C. Yeah. Huh?
I'm a little confused now because it's founded in 1976, but like Castelnuovo is when you're equal to the lower bound, right? So, but you didn't prove that until 1994. So, what was he looking at?
Huh?
Why was Scott looking at Castelnuovo triplets
Yeah.
if Castelnuovo polytope wasn't defined until recently? What was he looking at?
You very recently.
What?
Huh?
Do you understand the question? Like you said the Castelnuovo polytope is very new.
Very new, yeah, because after Kawaguchi, yeah.
So what was Scott looking at?
Oh, yeah, Scott, Scott wants to find, no, Pick's formula, based on Pick's formula.
Okay.
Yeah, Pick's formula. And the question is what can be said about the number of lattice points in the boundary and interior in general. Yeah. If number of lattice point, if number of lattice point in the interior C is 0, C is 0 case will be any number. What is the joke? Yeah. If C is 0, then any number is possible. Yeah.
Yeah.
And yeah, C is one case. C is one case is this, something like this. This is number 1. So this is number of lattice point to interior is 1 and 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Yeah.
Okay, so he was more interested in Pick's formula.
Yeah.
That's
Yeah. Okay, so and now this is okay. B in 2 cases. Yeah, C is bigger than 2 cases. B is between 3 and 2C plus 6. Yeah, between 3 and 2C plus 6. Yeah. Okay. And but so what can be said about this higher dimensional case? Yeah. But B equal C equal 1 case, just in this case, this kind of cases, many people to study this, so-called reflexive polytopes. Yeah. So we are interested in C's at least 2, and what is the higher dimensional case of this? This is the dimension. This is 3 is a dimension plus 1, and 3C plus 6. Yeah. Okay. So recall that. We know this. This is the boundary is D plus 1. Okay. And this boundary is CD plus 2D plus 2. And if D equals 3 case, if you put D equals 3 case, put this is 3, then exactly this is 2C plus 6. Yeah. So we know the simple fact, construct simplex and prism, we know if C equal to number of lattice point in the interior is at least 2 and dimension is at 3, B interior, then the trip BCD is Castelnuovo. If we know this, B is between this and this. And if D equals 3, then exactly this is 3. And D equals 3, this is exactly 3. So this is for 2-dimensional case, this is only if. This is a 2-dimensional case, this is only if. So the conjecture is something like the conjecture is this. This is the conjecture. This is if and only if. So we are working on this. Yeah. At least. Oh, this is interesting. Even if we prove this for dimension 3 case. Yeah. Dimension 3. Dimension 2 is true for Scott. Yeah. Okay. The final topic is smooth Castelnuovo polytopes. Yeah. So lattice polytope, lattice polytope of dimension D is called smooth. Okay. So if each vertex belongs to exactly D edges, this is 3-dimensional case. If each vertex belongs to the exactly D edges, Yeah. And each alpha one is a lattice point in this edge. Yeah. And which is closest lattice point to alpha on this edge EI. Yeah. And then this alpha 1 minus alpha d minus alpha, this is Z base of ZD. When this condition is satisfied, we call P's smooth polytopes. Of course, this is related with algebraic geometry, smooth varieties. Yeah. And Kawaguchi showed that every smooth Castelnuovo polytope of dimension 3 is reflexive. So in this case, reflexive is exactly interior lattice point is exactly 1. Yeah. And also this is some people Castelnuovo and he proved in his master thesis. So there exists no smooth reflexive Castelnuovo polytope of dimension 3 and dimension 4 and 5. So he proved this. Yeah. Because there is some program find all smooth reflexive polytopes. So by computer, yeah. So okay.
So do we know about dimension 6, or was that just too big to compute?
Oh, yeah, too big computer. But in principle we can do. We can do. Yeah. So big conjecture is this. Yeah. There is exactly no smooth reflection Castelnuovo polytope of dimension bigger than 4. This is also another interesting question. But this might be smooth varieties. I think there are some classification of smooth varieties. Maybe we can use some old results on algebraic geometry to prove this. Yeah. Or directly we can prove this. Yeah. In the language of polytopes. Yeah. Okay, that's all. Thank you very much.
Are there any more questions?
Oh.
So,
Oh.
for the people.
Okay. Oh, yeah.
Yeah, thank you for the talk. In the cases of, let's say, smooth reflexive
Smooth reflexive?
So I guess what I'm wondering is, for a finite class such as smooth reflexive polytopes, which are not Castelnuovo, do we have a sense of the discrepancy, how far they are from being Castelnuovo?
Oh, this is really compute the volume.
Mm-hmm.
Yeah, volume. Yeah, Castelnuovo, the volume is the smallest.
Sure.
Yeah. So some volume is bigger.
So I guess
far from Castelnuovo.
do we know how far away they can be? Like, is it bounded amount by dimension, or is it just arbitrarily large?
Of course, if you fix a number of lattice point in the interior, the volume have some upper bound.
Okay.
Yeah. So some upper bound.
Okay, that makes sense. Thank you.
Yeah.
Yeah, so thanks. So I have a question about the non-smooth reflexes.
yeah.
Are there any examples known where it's Castelnuovo?
Everything is non-smooth.
If it's non-smooth?
It's not smooth. Simplex is not
No,
smooth.
I mean
It's
for
not.
reflexive, sorry.
Huh?
For the reflexive of dimension 4, you said there were no smooth ones.
Reflexive case.
Reflexive of dimension 4, you say, right there, that there's
Castelnuovo
there are
dimension
no
is
smooth
reflexive.
ones.
Yeah.
So how about what happens in dimension 4 for other reflexive?
So
Are there any known that are Castelnuovo?
we do not know.
Oh,
Yeah.
okay.
Yeah. No. Yeah.
Okay, cool. Thanks.
Yeah.
Are there any questions for anybody online? No? Okay, any more questions from the audience? No? Okay, well, let's thank Takayuki again. Thank you very much.
Thank you very much. Yeah, thank you. Yeah.